All right, so what we've been doing up until now is creating these different building blocks and understanding them. These are basically just, you can think about them as Lego blocks that you can use to make more complex circuits. And the first step, the next step we're going to take, and we've started taking, is basically building op-amps. So we'll start building op-amps and we'll try to kind of, and we'll see how the progression of that process. So what is an op-amp? But if you think about an op-amp, really, an op-amp is a device that has a differential input and a single-ended output, and it has some substantial gain, right? And you want, generally speaking, if it's a voltage amplifier, you want the input impedance not to be too low, because it's sensing voltage, and you want the output impedance not to be too high, being able to drive, particularly if you're driving resistive load. If you're driving capacitive loads, then you can live with a high output impedance. So the simplest stage that we had in terms of a differential to single-ended conversion was the stage that we extensively discussed, which was a stage like this. So you have a differential pair, and we've looked at this extensively, with a tail current source. And then you have a current mirror off the top. So let's make a rail here and a rail here. Just make this clean a little bit. That basically reflects this mirror. And we know exactly what the gain of this thing is. We've discussed this extensively multiple times, so that should not be a surprise. So what happens here is that you have this stage, so this is your differential input, and that's your output. Now, we know the gain of this thing is basically the GM of one of these transistors times the RON and ROP. Those are the impedances you see across here. And we have even calculated some of these numbers, ROP and RON, and it's driven by GM of these guys. We also know that if you have a fully differential signal, this is VID over 2, this is negative VID over 2, and what it does is that it induces a current GM VID over 2, and if you flip the sign, this would be GM VID over 2. This current would be reflected here by the current mirror if the ratio is 1:1, which typically is in this stage. This becomes VID over 2. There are two that are injecting current into this node, and that current gets multiplied by the total resistance from this node to ground in differential mode, which is the parallel combination of those two. So the gain becomes GM RON parallel ROP. So we're familiar with it. So this is simplest op-amp, really. This is an op-amp. And you may rightfully say, okay, how about this thing? Well, this is not a real component. And you're absolutely right. We can turn it into a real component. Again, if you want to have a simple one, you can use an MOS here and say, okay, if I want to make it really simple, I can even have something like this. And if you want to make it more sophisticated, which you will, you can have more sophisticated current sources here, references that are independent of things. But let's look at this from a slightly different perspective now. One of the things that we want to look at is, okay, what is the range of operation in terms of voltages that, for example, the input of this thing can have? But when I say range of operation, I mean, in particular, common mode voltage. So let's say you're not applying any differential voltage. What is the range of common mode voltages where this is operational? Well, we can find out. Basically, the requirement here is that you need to make sure. So let's say, for the sake of argument, let's say it's a single supply. So let's say 0 and VDD. It could be negative, positive, et cetera, et cetera. It doesn't matter right now. But for example, we want to see how low can this voltage, the common mode, be before things start going bad. And what do we mean by going bad? Meaning basically transistors leaving the pinch-off region going into triode. Transistors that were not intended to be in triode region going into triode. And what's the problem, for example, if this transistor or that transistor goes into triode region? What would happen? What's the problem? Why is that an issue?
It's no longer solely dependent on gate source voltage.
Right. I mean, it becomes less dependent, and it will exhibit itself, manifest itself as RON dropping significantly, for example. The output, because now you're seeing the channel. You're seeing that resistance, right? You're seeing this part of the slope. So if you look at the IV characteristic, there's this flatter part which has higher outputs, and you're starting to see this part. And this has a low resistance. The gain will start dropping significantly. So that's not a good thing. So obviously we want to maintain that in that region. So what is the range? So what is basically we have to see when, and if this, for example, starts crunching, meaning that essentially it goes into triode region, then the output resistance of this guy will start dropping, the common mode rejection ratio will start suffering, and things will go bad, right? So what is the lowest this can go? What is the minimum this can be before that happens, according to our first order simplified model? Gate overdrive, exactly. Delta VGS, right? Let's call it delta VGS. I don't know, it's delta VGS really some 5, but some delta VGS, right? So this is the lowest it can be. So now, based on that, can we determine what is the lowest voltage this guy can be before that crunches? 2 delta VGS plus a VT, right? How did we get that? Because this voltage is going to be a VT plus delta VGS of this guy. Right? Let's call delta VGS 1. Delta VGS 1. Okay? Now, therefore, this guy cannot go lower than VT plus some 2 delta VGSs, or delta VGS 1 plus delta VGS 5. Right? So the minimum, V common mode minimum, is really VT plus delta VGS 1 plus delta VGS 5. Now, numbers, let's say, put some numbers. So this is, let's say your VT is 0.6 volts. And let's say your delta VGS is 0.3 or 0.4. Let's say 0.3 volts and another 0.3 volts here. You're looking at what? You're looking at 1.2 volts. So the input common mode of the input, or essentially, the input voltage cannot go below that, because if it goes below that, essentially, then for even one of the terminals, if it goes a little bit below that, then you can start crunching this guy, and things will start suffering. So now you can imagine this may not be very convenient if you're running off of a small supply voltage. Let's say you're running off of a 3 volt voltage, or even worse, 1.5 volt voltage, right? Then your range, your input range is very limited because you can't go down. But again, if you're a 3, the low end of this thing is limited, right? So that there's a limit set by this. Now, how about the high end? How high can it go? So what is the V common mode maximum? What determines that? Well, if you grab these two and push them up, right, what would happen? This voltage, remember, this voltage, this node voltage, will essentially primarily follow the larger of these two voltages in large signal. In large signal, if I grab one of these and start pulling it up, this one will follow that, because more and more current will go through it, and then you have the VT plus delta VGS of this thing. But now if I grab both of them and pull them up, that's fine. This will pull this node up, so this guy will be happy. Nothing will happen to this. This will actually get more and more headroom, right? And these guys are going pulled up, pulled up, pulled up. What happens? At some point, this will start conflicting with this. So one of these guys will start crunching. So what is the lowest, or what is the highest this voltage can be before this one crunches? VDD minus delta VGS, right? Minus delta VGS. Let's call it delta VGS 3. Right? So if this is the maximum it can be. Now, for this to be at that maximum, what would the common mode have to be? Think about what the common mode has to be for that to happen. Well, think about it. This guy is being pulled up, up, up. This will follow it. This will be a VT plus delta VGS below, right? This is the VT plus delta VGS. This is the gate source. So if I pull this up, this will be delta VGS below. And this guy will be a delta VGS above that, at the verge, on the cusp of going into the triode region. So this guy will essentially be what? A Vin minus VT below on the cusp, right? Because this is a VT plus delta VGS, and then this is a delta VGS. So this would be Vin minus VT. So basically, the constraints we have is that Vin minus VT, this voltage has to be greater than Vin minus VT. Or let's call it, on the cusp, it's a V common mode max minus Vt. And therefore, you can easily see that V common mode max, or in the case of max, it would be equality. It becomes an equality because it's maximum. Would be VDD plus Vt minus delta VGS free. And if you put numbers on it, you're looking at whatever the VDD is. So let's say VDD plus 0.6 for this example that we picked, minus 0.3. So in fact, this can actually go even above VDD, this input in this example, without actually anything crunching. So you can see that this stage has a fair amount of room to operate in the common mode range in the higher end. So for high voltages, it's fine. But it's not good for low voltages. So what would be a good thing for low voltages? What kind of variations? Remember this principle, that this is actually a useful and important principle, that you can take, essentially, if you have complementary devices, you can take any stage and flip it upside down and change the NMOS to PMOS, and PMOS to NMOS, or P devices to N devices, and vice versa. But that relies on availability of complementary devices. That may or may not be the case, depending on what technology you're operating in. But anyway, so what if we do the complementary one? What is the complementary one like? Let's do the complementary one, right? So the current source will be on the top, right? This would be the current source. This guy will go there. You have that current mirror. This is the resistor. Now you have a differential pair, which is made out of PFETs. And then you have the current mirrors. Now they're made out of NFETs. And you can make this one, and this is your output. So this is your differential. This is your differential input, right? And now you can imagine we don't need to. Yes. No. So, go ahead. Why can't delta VGS1, this one, can go below? Why is this, right? You're asking about where did this come from? Yeah, okay. So think about it this way. If that happens, if it goes below that, this one will start going into triode region. Why? Because if this is, let's say, 1.1 volt, for the sake of argument, let's say. If it's 1.1 volt, less than 1.2 volts, then you drop a VT plus delta VGS. In our example, we assume that VT plus delta VGS is 0.6 plus 0.3, so it's 0.9. So you go to 0.2, right? So this voltage would become 0.2 volts, right? But you need, in our made-up example, we said we needed at least 0.3 volts for this to stay on, because if the delta VGS of this guy is 0.3, then you needed a 0.3. So you actually have gone below that. It pushes this guy into the triode region.
But why wouldn't instead there just be a smaller delta VGS drop across the...
Because the delta VGS drop is dictated by here, right? By this guy. So the delta VGS is, so see, this is in this example, I mean, the MOSFET is even easier to see. I mean, it's true, in bipolar things can happen because there can be current flowing through in this direction. But what happens is that this voltage, this is a capacitor, there's no current flowing, right? So the only current that's flowing here is through here. If I remove this connection, this voltage is whatever it is, set by this voltage source, this resistor, and the W over L of this transistor, right? So now if I connect it here, I'm not drawing any current. So it's not going to change, even if it's in triode region. So this delta VGS is fixed. So this VGS is fixed, which basically means that the delta VGS is fixed, because it's VGS minus VT, right? So the minimum delta VGS that you can maintain is fixed while you're in pinch-off region. So if you go below that, you will end up in the triode region.
But what about the delta VGS of the first transistor?
This one will not change. You mean this transistor or this transistor? This one. What about the delta VGS of that? Well, the delta VGS of that is dictated by this current, right? So let's say if I make it common mode, which basically means that I've shorted these two to each other, They both have this, they are connected to the same gates, and source are the same, right? They have the same gates and they have the same source voltage because they're shorted, right? So they're in parallel. So they will have the same delta VGS. There's a current flowing through here. That current is going to be, if they're matched, it would be equally divided between these two. So there's some sort of delta VGS will be maintained. As long as they are, I mean, that will be maintained for that current. And assuming that this voltage is not too low, they are going to remain in the pinch-off region. Okay? Right. Let's look at some more examples, and if you are not convinced, feel free to ask more questions. So here, how about this one? What are the limits on this? Do you think, where would it be good at and where would it not be good at? Should be kind of trivial extrapolate. So this guy, this one, the one on the left, was with the NFET inputs. It has a common mode range that can go high, even above VDD. It has problems if the common mode range is low, right? And you can see this one is the opposite. So this one has no problem going down. This can actually go even below, the common mode can be even below the lowest potential here. In this case, is 0, or negative VDD, or whatever you set it to. But it has a problem going high because as soon as it starts going high, it's just crunching this guy. So each one of them has an advantage. And now, depending on what you're trying to design and what you're trying to do with the op amp, you can actually make a choice. Do you see any advantage other than that? Let's say you didn't care about that, or you were both okay with both of them. Do you see an advantage to one over the other one if this was your entire op amp? Yes?
The MOS is probably faster.
Okay, faster. Faster is one, yeah. We'll talk about faster later, but other than faster, do you see any other advantage? Do you think their gains would be different? If I use the same device sizes, the same N-type, NMOS, and PMOS device sizes on both of them. Let's say I use the same currents to bias them, the same device W over Ls for NFET and PFET. Would they have the same gain or different gain? Yes, that's right. So because this is GMN, right? And here you will get GMP. The gain of this guy is going to be GMP RON parallel ROP. So what happens typically, because the mobility of the holes is smaller than the mobility of electrons, on the same W over L and the same current, this would be less than that, and therefore this would get you less gain. Now, if this is your entire op amp, obviously you want to have, if you could operate under, I mean, both of them are okay as far as the range of operation, voltage range of operation is concerned. This would have some preference. I mean, there would be a preference for that because that would give you more gain. So again. So that's one of the things to think about. Now, of course, the next step is to increase the gain. And again, we talked about this before. So how do you increase the gain? There are several ways. If you're trying to make a single-ended output, and of course you have always differential input, but single-ended output, you can actually make a single-ended to differential conversion with cascode, right? And we did this last time quickly. But so here you could do that, and we'll do it in a second. Now, but in general, by the way, remember, there are op amps that are differential output. And if they're differential output, you can always use just basically the active loads and have the two sides equal. But we are focusing on single-ended output op amps because they're a little bit more interesting and complex. But again, there's nothing fundamentally different about them. So if you wanted to use the cascode, so this is the idea, right? I mean, we've seen these stages, so we are going to go through them quickly. Maybe I should leave a little bit more room here. So let me just draw my rails. And then starting with a current source, you can actually have and then we have a cascode stage, basically a common gate. And then you have the cascode current source to match the high impedance that you get out of that. Okay, nice. And then you can do something. The simplest form is this. You have the differential input, and this guy is sitting here. So you have two NMOSes and two PMOSes. If this were properly biased, so you need to provide some bias, the bias here. But if it's properly biased, then you can have the same operation. The same kind of calculations apply here, right? I mean, when we did a little bit of that, you can actually try to kind of like reference this, for example, to this node. There are different ways to do this. One of the things that you can do, for example, is to kind of have a diode-connected device here that's driven by a current source connected to the supply. Let's do it this way. Let's put it on the side. So I'm going to show it as a current source here. And if you choose this W over properly, we saw that you could actually make this W over L 1/4 of that, et cetera, or different values of this W over L. And there's calculations you can make to make the operation, DC operation, properly working. So you will have something like this that's self-biased. Now, of course, this current should not be as large as that current, right? Because what happens if this current is as large as that current? Let's say this is I tail. Now, this has to be a small fraction of that, I would argue. What happens if it's exactly the same? There's no current left for the differential pair, so all the current goes through here, through this device, and through this here. Done. Right? There will be nothing. So you will make this a small fraction of it. You can, make, for example, make it 1/100th of an I tail, or 1/10th of an I tail, or 100th of an I tail. Right. Yes? Why share I tail? Because if I don't share it, so that's a good question. So what's the alternative? Let's think about it. Again, there's no single correct answer in design, right? So this is the one pathway we've taken. So if I were to do this and have a separate I tail 2, right, is that what you had in mind? Okay, so what would happen? How would the purpose of this device was to establish a voltage here, right? Now, think about it. What happens if I, instead of doing, this is a good question, actually, so let's talk about this a little. So correct me if I'm not drawing what you're suggesting or what you're thinking about. So doing it this way, biasing it through that. Is that your proposal? Yeah, I mean, by the way, so if that was the proposal, we don't really need one of, well, we have to get rid of one of them anyway, right? So let me ask you this question. What determines this voltage? Well, right now, the way I've drawn it, VDD determines the voltage, so that's not good because it's shorted to VDD. So I should put the I here. Let's say I bias 2, right? Do you see the problem there? Because now, if I do it this way, what is this voltage? It's referenced to here. So this voltage is going to be VT plus some delta VGS of this guy. So yes, I can establish some fixed voltage. I can do it with the diode connector. I can even do it with the resistor, etc., etc. But then this voltage will be fixed, right? Do you want this voltage to be fixed, or do you want this to be moving with your input common mode? You want it to be moving. Why? That's correct. Why?
It's got to be able to move up and down to maintain the same gate source differential as the differential.
Right. What happens if I do this? What happens if I fix the voltage? You say, well, this voltage is fixed at whatever voltage, like 1.2 volts.
You limit how high DC.
Yeah, I limit basically my common mode range, because then this voltage will dictate this voltage, right? And this voltage dictates how low this voltage can be. The drain can be here, right? And what that does, it basically doesn't let it, I mean, so then you basically are limited. Now, the way we were doing it before has the advantage that this is basically moving up and down with this common mode. Because as I change my common mode, so if I go back to the original pathway we were exploring, and put some sort of a transistor here with some W over L that needs to be determined based on that current, and provide a current, IB2, let's call it, to VDD, then this voltage is basically tracking this lower source voltage. So as you increase your common mode or decrease, this voltage moves up and down with it because it's a VGS below that, right? And then this guy will be above that by a certain amount. That's determined by this current and the W over L of that transistor. So it has the advantage of allowing this to be tracking the common mode of this thing as opposed to being pinned to a fixed point. But it's really good that you're thinking about these alternatives. Right? That's really good. I mean, that's exactly what you should be thinking about, because that's how new designs are created. So yeah, we should continue thinking about them and seeing, okay, what does each one of them do? And you can actually propose, feel free to propose, hey, why aren't we doing this? Or what happens if you do this? If something that say, oh, we could do that instead. How about that? And that may be a valid answer. And like everything else, there's usually a pro and con. There's always a trade-off. So, well, yeah, that's advantageous from this perspective, but it will hurt you from this other perspective. So anyway, so if we do something like this, let's try to kind of like push it a little bit farther and get a sense of what this op-amp looks like. So you can see that we are adding complexity to it. There are different ways to deal with this. Sometimes we would like to actually keep these abstract, right, these current sources, because we know how we are going to make it. You may see op-amps inside op-amps, right? And it's not it's the same deal as recursion. The op-amp inside the op-amp is simpler. It's a simpler op-amp than the full op-amp. So eventually that stops at some point. But now here's the thing. But if, just for the sake of argument, let's make this fully based on transistors. So let's express every transistor in this example, just quickly, and see how it works, how it looks. So how do we make it current source here? Well, this current source will have to be an MOS transistor. You can actually make it out of some sort of a current mirror. And now you have to provide some pathway for this current mirror to be biased, right? So this needs to be provided. So now let's try to make something a little bit better. What would be a better thing that would not depend on the power supply, for example, as a reference current? Let's make a reference current. We've built these things before, right? You know, we talked about this kind of like supply-independent biasing and things of that sort. So it's a MOS process. Let's say I don't care too much about temperature variations and things of that sort, but I want something that doesn't depend on supply. A threshold reference, right? A voltage that's related to a threshold voltage may be a good thing. How do we do that? Well, to refresh your memory, there are varying ways of doing it. A simple one would be to use a floating mirror. And take there are many different ways to do this. This is a easier to see way of doing it. So you basically take another transistor, you make it W over L, and here what the voltage you get here is VT plus delta VGS of this guy. And you make this W over L, and you make this W over 4L, or basically W over 4 divided by L. That's a better way of saying it. And this is an R. And you remember why we did this, right? Because if this voltage was VT plus delta VGS, this voltage was what? VT, 2VT plus 2 delta VGS, right? Right? VT plus VGS here, delta VGS here, VT plus delta VGS here, right? So it's the sum of the two, so you get twice as many. And then if I make this W over L, W over 4, what would happen to its delta VGS for the same current? The delta VGS doubles, right? Because its delta VGS is square root of what? ID over mu n Cox over 2 W over L. So if I make this W over 1/4, my gate overdrive for this guy has to be doubled. And the reason we did that is that now here we just get the VT. You get rid of the delta VGSs. You get the VT without the delta VGSs. You cancel the delta VGSs. And then you basically do this. Now, depending on how much, assuming that, well, if you have enough headroom for all of this stuff, then you will have headroom for a cascade version, which would be maintaining things more accurately. So you can have a cascade isolator, and then you can have a cascode mirror. The mirror forces the currents of the two branches to be equal. That's what it does, right? And I got to be careful here about how we do this. So I can put these, for example, on this side, and those on that side. Why didn't I put these on this side? You remember?
You wouldn't have a low impedance.
Yeah, I will have a low impedance path between VDD and ground. I will have like 5 diode connected transistors in series. Right? So what happens here is that you basically have created this, and then so this is your reference branch. And you can make it so that it has the current that you want. I mean, and of course, you usually make this much smaller than that because you don't want to be spending as much current on the reference branch as everything else, right? So, and then you can copy it. You can replicate it here. You can take this, for example, if you want, and make a copy here that would go and drive this guy. Okay? And we need to make this one too, right? How do we do that? Well, it's a different branch with a different current, so the W over L of this one would be different, but essentially, this is what it is, right? Now, of course, this W over L, I don't know, is going to be different from that W over L. Much smaller, probably, because you are trying to produce a current that's much smaller than that. Right? And you can go and adjust the W over L to get the DC level right, and then you will have something that will have gain as long as there is no resistive load. Because as soon as you put a resistive load, all of this is going to go haywire, right? Because you remember, this is, let's give them numbers, I don't know. Let's say call it M1, M2, M3, and M4. So this is going to be RO4. This output resistance is roughly GM3RO3, which is the maximum intrinsic gain of this guy, times RO4. So the RO4 gets multiplied by that. Same deal here. This is going to be differentially RO1. And this is going to be the maximum intrinsic gain of this guy, which is GM2RO2 times RO1. So the output resistance is the parallel combination of these two times the GM of these guys, which is dictated by this, and the W over L of these transistors, so you can get whatever gain it is. We can actually calculate it. Let's just put some numbers down, just to get a feel. So let's say mu n Cox is 100 microamps per volt squared. Let's say mu p Cox is 50 microamps per volt squared. Let's say dxd dVds for both n and p is like 0.05 micrometers per volt. Now, these translates to certain numbers, right? I mean, so we need to pick some sort of a current. Let's try to make these branches, and let's say VT, the threshold voltage is, I don't know, 0.5 volts. I think those are the things that we need for this calculation. So first we need to establish a reference branch here, right? How do we establish the reference branch? Well, we are trying to find something that works, that produces some current, and it depends on what kind of current we are trying to determine. Because in this case, this current is going to be VT divided by R. Let's say we make a reference branch that's, let's say, at 10 microamps. Let's say we're trying to make it at 10 microamps. So we are trying to make this number 10 microamps. So let's see if we can do that. So for this to be 10 microamps and VT of 0.5, what do we need to have? So it's 0.5 volts divided by 10 microamps. What do we get in terms of resistance? If it was 1 volt divided by 10 microamps, it would be 100 kilo ohms, right? So this would be 50 kilo ohms. It's a pretty large resistor, but let's say we use it. Okay. Now, how about the W over L of this guy? It really by itself doesn't matter that much but if you're trying to make it low noise and you don't really care about some of these properties of these things, then you need to really think about how you make this. So for example, make it relatively large. Let's say you make it 10, or let's say, yeah, 100 micron, well, let's say 10 microns over 1 micron. And we'll talk about noise and all those things later. We don't want to make it too small for that reason. And this needs to be a 10 over 1. This would be a 10 over 1. And you could do the same thing for the rest of them, really. And here you can do the same thing, or you can have actually something a little bit larger to make up for the smaller mu and Cox. Something like that. Again, this is not optimized or something like that. Yes, Al?
The one above the resistor should be smaller.
Oh, you're right. This should be 1/4 of that. So this you're absolutely right. So this should be 2.5 divided by 1. Thank you. Yes. To get rid of that extra delta VGS. So this is some sort of a set of numbers. And then we still want this reference branch to be 1-to-1 with that. Now we are starting to see something interesting. So we can actually see, for example, that this reference branch would be also at what? Let's say 20 over 1. So you get the same amount of current. You get the 10 microamps here. Now, here, you're trying to basically get probably more than 10 microamps. Let's say you want to have 100 microamps per transistor in balanced case. So that means that this tail current needs to be about 200 microamps, right, roughly. So to get 200 microamps here, you're trying to get 200 microamps here. It means that this ratio, and if this branch is still carrying 10 microamps, this ratio needs to be what? The ratio of this W over L to that W over L needs to be 20, exactly. Now, you could, for example, depending on what you're trying to, so what the simplest thing you could do is they say, look, you know what, I can make this still a 10-to-1, and this becomes 200-to-1. That's a possibility. It may have it, so here's what one of the trade-offs there involved. You may say, okay, well, this is a pretty large transistor, 200 microns. Of course, you don't make it out of just one gigantic 200 microns, right? You make it out of a large number of shorter fingers in parallel. But if it's 200 microns, you may say, this is quite large. This capacitance may become large. This may have some effect on the high-frequency behavior. So you have a trade-off. You can make this smaller and that smaller. Instead of a 200 over 1, you can have a 100 over half. Assuming that what your process allows you, what the minimum channel length is. But when you do that, you are compromising something, right? And you need to do the same thing here too, right? You need to make this, whatever, 5 over 1.5 or something like that. But what is the trade-off? What happens if I make this L shorter? What does this L determine? The output resistance of this guy, right? And common mode rejection, exactly, because your output resistance is going to reduce and your common mode rejection is compromised because of that. So there's a trade-off there. Sure. Let's keep it the way it is right now. It's fine. Now, you're talking with something like this, and then but these guys, now here is where you need your GM. The GM here matters, right? Yes?
You just cut the 20 and 10 on the near there so that you don't have to go as high as 200?
20 and 10. You mean?
Yeah, cut those to
let's say for the sake of argument, if I make them 1 and 20, that's an extreme version, right?
Well, I mean, cut the PMOS on top of the same.
You don't need to. So you don't need to cut this one, right? Because this needs to be matched with that, right? So what you suggested is sound, but it's another trade-off. Let's see what that trade-off is. So if instead of 10 to 200, I go to 1 to 20, what would happen? What's the thing? What am I trading with? What? Right? What is the trade-off now? What does reducing this W over L do? I didn't change the L, so my output resistance should not change, right? So output resistance is not affected, but something else will be affected. Delta VGS, right? So now, when this could, for example, go down to 0.3 volts, now it needs to go to like 0.7 volts before it crunches. I mean, so now you're losing headroom here. You're trading with headroom. Do you see that? So there are trade-offs here. So I'm just going to keep some numbers. I mean, these are, like I said, I mean, there's nothing optimum about anything we're doing here. Just like it's just some set of numbers to get you a sense. And of course, then you need to be looked at and optimized. And this, if you plug this in, it may not be really very good anyway. But let's start with something. You have to have a starting point, right? Usually that's the hardest part when you're designing or creating in general, right? Creating from clean slate, a blank sheet, is usually the hardest thing. Right? So once you put something down, you can say, okay, I can work with this. Oh, it has this problem. I can change it, and it evolves into whatever the final thing is. Okay, so let's go through this process. So let's see, what do you do with these guys? Now here, for these guys, you need GM. The GM of these guys matters, right? So here you may want to actually consider using your shortest channel length. Because both the speed matters, because you don't want to introduce a lot of capacitance. So you don't want to be making large W and Ls. And you want to have a large ratio of W over L, which basically means that use the smallest product and largest ratio that you can use. Now, for every process, there's a minimum channel length that you can use here. You may not want to be at minimum, for example, depending on what your other requirements are in terms of noise and all those things. But let's just say this could be like, I don't know. I mean, it depends on the process. So this can be a pretty small number, right? I mean, so let's say make it a, I don't know, 0.1. micron, 100 nanometers, right? And then you want to make this probably a 10 over something like that. I mean, or depends on what you're trying to do and what your process gives you. So this can be actually a pretty high transconductance device with relatively low capacitance. And if you're using things like that, you're probably not going to be deviating too much over those. So you probably may end up having the same dimensions or slightly different dimensions here. And then here, I have to be careful though, right? Because now if you do just that, if I make it that small, what am I going to compromise now? Are we going to gain necessarily? Not necessarily, right? If I just use that. Why? Because now what happens to my RO? Let's calculate our RO for 1 micron and 0.1 micron based on the numbers we have. So the ROs, let's say RON, well, RON and ROP would be the same. And we are making the currents to be 100 microamps each in the balance case. So RO is going to be L divided by I d dxd dVds inverse. So you are getting, for 1 micron over 100 microamps, and here you have a 1 over, or let's say 1 volt over 0.05 micrometers. This cancels that, this over that. Basically, so you get, what do you get? So that becomes 5 microamps. So it becomes 1 over 5 microohms, which basically becomes 200 kilo ohms, right? At 0.1 micrometers, this will scale down to 20 kilo ohms. So for these guys, this is going to be 20 kilo ohms, and that's going to be 200. Oh, no, sorry. But this output, for example, is going to be 200 kilo ohms. The output resistance, right? Roughly. So let's see, what do we get? Let's go through the process and get a little bit more. Yes?
So why would you want your cascode amplifier or your cascode transistors to be larger?
That's a great point. This doesn't need to be this small, right? Another trade-off, though. If you make this very large, because you need to, so can I just scale, what happens, so there are two directions we can go. I can just scale this guy. Let's say make the L 1, back to 1. It would improve it because then this term is going to improve, right? To some extent, because its GM is going to reduce. But it's going to reduce as a square root, but this is going to grow as a linear, so it's still an advantage. So, but what else do I compromise if I just do this? My W over L has become smaller. For the same current with smaller W over L, my delta VGS is going to be larger. So I'm losing range of operation, right? Now, you may say, okay, how about, well, you increase the W2, make this 100. So the ratio is the same, but L is larger, so you get the same GM, and you get 10 times higher RO, so you get a factor of 10 improvement in your RO. What did I lose in the process of doing that? What did I compromise? Oh, of course, you have to do it on both sides, right? What did I compromise? What did we compromise right now? Speed, which we haven't talked about, but then you're making this capacitance on this node larger, and you're losing on that. So this is exactly what design feels like, I mean, right? I mean, it's like you feel that there's no, if you feel that something is just like, oh, this is like a free knob, I can turn it. It's like 9 out of 10 times you're missing something, right? There's something else you're compromising when that happens. And that's the way it should be. That's the way it actually is. A good design, eventually, is one where it feels tight in all directions, right? That's the nature of an optimum point, right? When you're close to an optimum point. Any direction. If you're top of the Mount Everest, any direction you go down, right? This any direction you walk. But anyway, so I mean, yeah, you're right. I mean, so there may be a compromise here. So this may end up being 0.5, 50 over 0.5 or something like that. And these are the things that you need to do quantitatively when you calculate the speed and all those things. And the same thing here. You can basically do similar things here. So you probably want to have a 50 over 0.5 as a for example. I mean, again, there's nothing magical about the numbers I'm putting down here. And probably they're not optimum. Well, they're definitely not optimal, not probably. Okay, something like that. And then you have to also, last time we talked about, we have to think about the startup. So you may need to create a branch here to kind of like make sure that this turns on, because this has a stable state at 0 volts, at 0 current. So that you need to make sure that that starts. But this is an example, right? And this is a simple example. So now if I ask you, come and quickly ask you guys, what do each one of these transistors do? What is the role that they play? You should be able to tell me, right? So let's do it. So what is the role of this transistor? Say again, speak up. It's part of the current mirror here, right? That guarantees the equality of the branches of these two. So these 4 really are combination. What is the role of these guys? It's just forming a cascade with that, right? What is the role of this group of transistors, let's say? It's part of the floating part, the isolating. So basically they force these 2 voltages to be equal. Or if they were equal. So now we also kind of like modified it a little bit, so we kind of made it to a tweak so get rid of this voltage too as well. But if they were equal, then they would be floating. What role does this transistor play? Right. And what is this current used for? To generate a bias for that gate, right? What role do these transistors play? What are they doing? They're part of the cascade. Why did we use cascade? Increase the gain by this factor, right? What role do these guys play? They're the cascade part of the mirror, right? Right. So, and what are these two doing? Yeah, they're basically the current. So they can actually even calculate the gain, right? I mean, so let's see what the gain of this thing would be. So we didn't do that calculation. So what we have to calculate the GM. So GM and for this W over L would be what? It would be square root of 2 mu n Cox W over L ID. So it would be square root of 2 times 100 micro amps per volt squared times the W over L is 100 times current, which is 100 microamps. So we'll get, so I get a 100 microamps out over volts, and then I have a square root of 200. So it's like 10 times square root of 2. So that becomes 1 milliamps per volt times square root of 2. So it's 1.4 millisiemens. That's your GM, right? And if I ask you what's the gain, So now let's calculate it. And the GM of this guy is going to be the same. And same here because the W over L is the same and the current is the same, right? So it's going to, this factor is going to be what? Let's calculate this factor. This factor is going to be 1.4 millisiemens times, oh no, I have to calculate the new RO. So RO of this guy, so RO here is, so this RO is 20 kilo ohms, right? This RO, RO2 is going to be 100 kilo ohms, right? Because it's 0.5 now. So this is going, this factor, this is going to be 1.4 millisiemens times 100 kilo ohms. So kilo and millisiemens and kilo ohm cancel, so you have 140, so this factor is 140, times RON, which is 220 kilo ohms. That's a pretty large number, right? That's basically you're looking at 2.8 mega ohms, right? And here you get something larger because this RO4 is the 200 kilo. No, it's not 200, it's a 100 kilo, right? So 100 kilo ohm. This GM we have to calculate now because the GM, this is a GMP. Now, but we know it's going to be a factor of 2 smaller here, which basically gets rid of this factor of square root of 2. So it becomes just 1 millisiemens. So this is 1 millisiemens times 100 kilo ohms times 100 kilo ohms. So this is a 1 milli, the 100 times, so that becomes like 10 mega ohms. So you have 2.8 mega ohms in parallel with 10 mega ohms, whatever, 2 mega ohms roughly. 2 mega ohms times 1.4 millisiemens, you're looking at 2800 roughly. And this is a very rough calculation. So if you put this in SPICE, you may get something like, 3,500, or you may get like 1,800, 1,900. But it's the ballpark of it that you're calculating, right? So, and that's what matters. So you're getting in the range of 1,000 or a couple thousands, a gain of a couple thousands, right? So this is as far as we really can go. I mean, you may say, okay, well, I do a triple cascode, and I get another factor of these. But at that point, when you're going above mega ohms, a few mega ohms, your leakage current and second order things that you've ignored in your simplified model will come and kick in. And you may calculate something that's like 100 mega ohms. It's not 100 mega ohms. It's because that leakage current is going to dominate through the junction or reverse current of the junction or the surface currents, things of that sort. So a lot of things can come into play and limit you. So this is kind of like maximum you can get with this thing at best, right? I mean, just like maybe 1,000, a couple thousands, things like that. So what if you need more gain? Well, you can deal with that stuff. We'll deal with that in a second. But now let's talk about variations on this that may also be helpful before we try to get more gain. We also saw that we have these limitations on the headroom. You can imagine that the headroom limitations actually are more pronounced here, right? Because now you have 5 transistors stacked, right? So you have to really deal with that. You have to think about how you do that. So one of the things that's helpful in this is this concept of folded cascode. Right? And we've seen folded cascode. You've seen folded cascode in some of the problem set. The idea of a folded cascode is that, yeah, cascode is great because it gives you gain. Why does cascode give you gain? Because it has higher intrinsic output resistance, right? Now, that's good. And also cascode has a second advantage, which we haven't talked about and significant. When we talk about high frequency, we'll see that it's actually from a frequency response perspective, it has a certain, quite a bit of advantage actually. But the concept of folded cascode itself is a simple concept. So you say that if I have the regular cascode, which looks like this, so this is the input, this is the bias, and this is a load resistor, and this is your output, right? You now have 2 transistors stacked plus some sort of a load, right? The idea here is that you actually turn one of these guys, the common gate transistor, and use the PFET. And then you go to your load. Of course, since this draws current, we have seen this before, and this draws current, you need to have a current source flowing into both of them, so you have to provide some sort of I bias. Now, what is the disadvantage of folded cascode compared to the regular cascode? Well, correct. That is true. But let's say this one, if it's wants to operate, it needs to be drawing current too. You want to do the same thing?
Yeah.
Now, there is something else actually. So let's say you have 1 milliamp at your disposal. You have a budget of 1 milliamp for this thing to use, right? For 1 milliamp, which one do you think will give you more gain and why? This one, right? Because all of the 1 milliamp is going through this guy. But here, if you, for example, were to divide it equally, if you have 1 milliamp here, half a milliamp would go here, and half a milliamp would go there. So you have less current, less DC current available for this guy. So here you had 1 milliamp. So you get more transconductance here compared to there. Right? So you are basically, yes, you're gaining in headroom because now you have really one transistor. Well, really you have two because this is another transistor. And you have had to have two if you were to do it this way. But this can be this can be close to, this can be a small overhead because this can only go down to delta VGS. But the thing is that you now have two things that are sharing the same current. So there's a price. But if your voltage range is a problem, you have to deal with it, right? Now, there's an equivalent, there's a differential equivalent of that thing. So you can actually take that, for example, or any kind of things like that, and then you can flip the input. So there's a folded cascode variation of these op-amps, right? So the folded cascode variation looks like this. So you have your branches. And this time I'm going to show it, for example, as a fully differential output. So these are called telescopic cascodes, by the way, because they're like the old telescopes, the old that they use, just to extend it out and in. They can actually compress. The voltage is going up and down. There's like these different pieces are moving up and down with respect to each other. So you have something like this. Let me show them slightly differently here to emphasize the difference. Right? And yeah, that's fine. Now, what happens is that your differential pair really is here. So you can have a current source here to the supply going to an PFET differential pair that is coming in and driving these guys like that. So this is your differential input. So this is the flipped version of this thing, right? So let me just draw the flipped version of this thing. The flipped version of this thing looks like this. Does everyone see that this is the flipped version of that? Right? The inverted version of that. So now, this guy corresponds, these are the input transistors. So from a single-ended, from a half-circuit equivalent perspective, you get that. It looks like that, right? And then these two correspond to this. Again, in half-circuit, you will get one of them, right? And what is the role of these guys? What are these for? They are the current source. Right? So let me show it more precisely. This is that. You can do it. Draw a current source here. Let me draw a current source here. Right? Now you have to have a reference branch, of course, here. And these correspond to that, and that corresponds to this. This is just the equivalent half circuit. The one on the left is the half circuit equivalent of the one on the right. Okay? So you can do that too. Okay, so that's for the one-stage op-amp. But again, you're getting gains of thousands, right? What if we need gains higher than that, significantly higher than that, possibly? What do we need to do? Cascade the op-amps, right? Just basically put them in, basically make a two-stage op-amp, two gain stages. So let's do that. Let's go here and try to do that. Let's start with a very basic stage, very basic single-ended to differential to single-ended converter stage. And start with that and see if you want to make a two-stage op-amp, what do we need to do? So let's say this is our single-ended to differential differential single-ended, converter stage. And I need a second gain. So this is VDD, let's say this is 0, whatever, or negative VDD. We can do either one. So we know whatever gain we get from this one. And this can be cascoded or not. Let's just deal with the simple one because we don't want to make it too complicated right now. But now I want to add a second gain stage, right? What kind of stage can I use? The basic gain stage is the common source, right? So let me just put a common source down here. Don't take notes yet with an active load, because there's a problem with on drawing. So this can be a gain stage, right? I mean, this is my second gain stage, right? What is the gain of the second stage? If this current source has some output resistance, some sort of an ROP, and then this is the RON, and then there's a GM, so this current is going to be whatever, that's V1. This is going to be GM V1, so it's going to be GMN times RON ROP, RON parallel ROP, right? That's the gain. So from that perspective, that's okay, because then I get two GM RON ROPs, right? I get GM RO squared kind of thing, right? So if I'm looking at 1 millisiemens and 100 kilo ohms, then I'm looking at 100 around there, so I get a 100 squared, so I get 10,000. And if we go to cascode, you can get to 1,000 times 1,000 presumably and make this cascode and all those things. But there's a problem with this, the way I've drawn it. Can anyone identify a problem? Yes?
You need some like voltage follower, so something that changed the voltage.
Voltage level. So you identified the source of the problem. Let's talk about the source of the problem and then talk about solution. So the source, there's a problem. So if let's say nominally, what voltage is this? Let's say if this was balanced, if this were balanced, what voltage you expect this to be roughly at when the input is balanced? There's basically no differential input. If the currents are the same, right, more or less, then this VDS has to be the same as this VDS. So this would be roughly around a VGS below, or VT plus delta VGS below VDD, right? So it's going to be a little bit below. So it's going to be around the same point this guy is, mostly. So that's some voltage. You may say, but this needs to be a delta VGS above 0. So let's put some numbers down. If I put some numbers, let's say this is 5 volts and this is 0. Now, and let's say the VGS, so what did we say? This is 0.6 plus 0.3 volts. Let's make it 0.6 plus 0.4. So 0.6 for VT and delta VGS of 0.4. So that's going to be a volt below that. That's going to be around 4 volts, right? Nominally, when the stage is balanced. And this guy wants to be what? It's going to be VT plus delta VGS above 0. So it wants to be around 1 volt. So what is that going to do? So this one cannot pull that down, essentially, right? Because it has no influence backwards in the MOSFET, because it's not drawing any current. So it will be pushed way up to 4 volts. this guy goes into, this one starts crunching. This will go into triad region because it has a large VGS, and it basically just starts pulling this node down. It will go to ground and would not produce any gain because GM would be lower, but more importantly, the output resistance will be very low. So it's not going to work. So Alex suggested something interesting. He said that, look, put some sort of a follower to adjust these voltages. So let's say, what do I need to adjust it by? Let's go down that route. In this case, I need to drop another 3 volts, right? So if I put let's say magically I had a 3-volt battery that I could put here. Would that solve the problem? I mean, a follower is not going to be better than that, right? I mean, so let's say let's say magically I put a 3-volt battery, 3-volt voltage source in there. Would that solve the problem? Do you still see a potential problem, at least? It seems to kind of like, at least ostensibly, it has solved the problem, right? But there's still a problem. Tell me what the problem is.
Output impedance of the first stage is too large.
The output impedance of the first stage is large, but it's okay because it's driving a capacitive load in this case, because it's driving a MOSFET gate of a MOSFET. If you had a bipolar transistor here, yes, we have to worry about that. And we'll worry about it when we make a bipolar op-amps. But right now, it's okay. That's not the issue. It has something with the DC levels. The problem is still with the DC levels. What if your supply voltage changes? What if your supply voltage is not 5 volts? What if it becomes 4 volts? Then you're messed up, right? If your supply voltage becomes 6 volts, you're messed up. So you can say, well, if this supply is exactly regulated and well-defined in your circuit, yeah, maybe. But it's not a good design still because it's sensitive to that. Right? Because this point is reference to VDD and this point is reference to ground. Right? This is the way to think about the problem. The problem is that this stage is referenced to ground. For this voltage needs to be referenced to this supply, and this needs to be referenced to the top supply, and they can potentially change. And as soon as they start changing, then everything can go haywire, even if you had that 3-volt or perfect voltage source. So how do we do that? How do we solve this problem? Yes.
AC coupling.
Well, okay. So AC coupling. So that's an interesting suggestion. But it gets around some of the fundamental advantages of an op-amp. Because an op-amp, one of the important things is that it basically has to have gain at DC to maintain operation and feedback and things of that sort. So you can AC couple it, but you basically throw away a big advantage. So we are trying to not to do that. We're trying to stay away from that. Can you think it? So see, this is the way you should be thinking about when you do circuits, or a lot of things. Think about architectural changes, not just parametric changes that will help you. Because, parametric changes are the final stage of the design. Topology or architecture changes are important. David?
Could you replace the NMOS with a PMOS?
Yeah, exactly. Flip it upside down. Just apply this to a PMOS. Right? So do it this way. What if I had a PFET stage with an NFET current source? I'm just going to draw a current source for now to make it simple. And connect it this way. Now both are referenced to VDD. So now if my VDD is 10 volts or 3 volts, this issue is not going to appear, as long as I choose the sizing of these things properly so that at this, whatever this voltage is going to be. So it's not going to be dependent on the supply voltage moving up and down, right? Does it make sense? It's a simple change, but it's an architectural change. It's a topological change, right? That helps you solve that problem. Now, once you have this, now I will tell you one more piece of information that you may not know, is that from a stability perspective that we'll talk about when we talk about stability, and we'll see why that's the case, you want to actually have your second stage, this stage, to have more gain when you try to do frequency compensation on that and all those things. So are we having that situation? Are we in a place that out of these two stages, which one is the one that's giving us more gain in principle? Because it's this guy, because it has the N-type GM, right? So what if I wanted to get N-type GM here, the driver, which like what I drew first? But I don't want to have this problem. We don't want to have this problem. What do we do? What's the next step? Yes, exactly. Invert the whole thing. How do we invert the whole thing? Let's invert the whole thing. So this goes up there. This differential pair becomes a p-FET differential pair. And then you have an NMOS current mirror, which will go, now both of them are referenced to the lower potential, whatever, be it negative VDD or ground or whatever you have. And then you put it here. Of course, this is not going to be the way it looks. The way it looks is going to be a p-FET, and this is going to be another p-FET. Right? These are the current sources we are making. Then you need a current mirror reference branch. And then whatever your IREF is, however you're generating it, something as simple as a resistor or something a lot more sophisticated that will give you temperature and supply and process with independence. Okay. So now we have some sort of a more complete op-amp, right? And what is the gain of this op-amp? Last quick calculation. So it's going to be, what is the gain of the first stage? Well, the drive here, this is basically a GMP of this transistor, right? And then the output resistances are going to be ROP and RON. So the gain of the first stage is going to be GMP RON ROP. Of course, this may be different for this stage and that stage if the W over Ls are different, right? So you have to calculate it differently. And here you have a GMN that drives the RON, let's call this RON1, ROP1. And then this is going to be RO2, RON2, and ROP2. And then this is basically GMN2. So the gain of the second stage is going to be GMN2, RON2 parallel ROP2. Right? So the total gain is the product of these two. And this is a viable op-amp. Yes?
Since it has pretty high output resistance,
Uh-huh.
do you want to add a buffer? Is that going to
Okay, good question. So he says, Alex, so you're saying that, okay, how about the output resistance? If I put a load resistor here, this is going to kill it because it's going to be RON2 plus parallel ROP2 plus some sort of an RL. And if RL is smaller than those things, it would just be RL. That's true. This op-amp is not intended to drive, the way it's drawn, it's not intended to drive a resistive load. This is intended to drive a capacitive load. So this can be some internal op-amp doing something else, or to driving the next stage, which is also gates of another MOSFET or something like that. But you're absolutely right. If you want to have a resistive load, you need some sort of a buffer to present a high impedance here and a low impedance there. Right? So that's absolutely right. Okay. Any other questions on this? Okay.